Ever wondered why the ground beneath our feet, so solid and reliable, suddenly decides to shake, rattle, and roll? Well, let's dive in. You see, contrary to what you might think, our Earth's crust isn't one solid, unbroken piece. It's more akin to a jigsaw puzzle made up of large fragments known as tectonic plates. And these plates, they're not stationary. They're more like rafts floating on the semi-fluid layer of the Earth's mantle. This constant, albeit slow movement is primarily what causes earthquakes. As these plates interact, they can slide past each other, pull apart, or even collide. Now imagine two enormous masses of rock grinding and pushing against each other. It's a pressure cooker situation. Eventually something has to give, and when it does, the energy is released in the form of seismic waves, causing the ground to shake. So the next time you feel the ground shake, remember, it's just the Earth doing its own version of the tango. Now you may ask, how does the movement of these plates cause the ground to shake? Good question. Let's dive right in. Imagine the Earth's crust as a giant jigsaw puzzle. The pieces of this puzzle are what we call tectonic plates, and the edges where these plates meet form breaks known as fault lines. Now, these plates are not static. They're constantly in motion, sliding past each other, but they don't always have a smooth journey. Sometimes they get stuck. Think of it like trying to slide a heavy piece of furniture across a rough carpet. It doesn't move easily, right? The friction holds it back until you apply enough force to overcome the resistance. Similarly, the friction between the tectonic plates holds them back, causing pressure to build up over time. And what happens when all that pressure is finally released? Well, the ground shakes and voila, you've got yourself an earthquake. But wait, there's more. When an earthquake occurs, it doesn't just cause the ground to shake, it also sends out waves of energy, known as seismic waves. Picture dropping a stone into a pond. The stone creates ripples that spread out from the point of impact. Similarly, an earthquake generates seismic waves that radiate out from the epicenter, shaking the ground as they move. These waves are the reason why earthquakes can cause such widespread damage, and why you can feel an earthquake's effects far from its epicenter. They're also what scientists use to locate the epicenter of an earthquake, and to measure its magnitude. So, an earthquake is essentially the Earth letting off some steam after a hard day's work. Now, not all earthquakes are created equal. Some you might not even notice, while others can bring cities to their knees. But how do we measure them? Welcome to the world of seismographs and the Richter scale. You see, when the Earth decides to do a little shimmy, it's not just about feeling the ground move under your feet. It's about seismic waves, and capturing these waves is where a seismograph comes into play. Picture a pen attached to a weight, scribbling away on a roll of paper. When an earthquake hits, the ground moves, but the weight, it stays put, thanks to our good friend inertia. This difference in motion is what our pen records, and voila, we have a seismogram. But how do we make sense of these squiggly lines? Enter Charles Francis Richter and his Richter scale. This logarithmic scale assigns each earthquake a magnitude, a single number that gives us an idea of the energy released at the earthquake's source. The kicker? Each whole number increase on the Richter scale represents 10 times more ground motion and 31 times more energy release. So a 5.0 isn't just a little stronger than a 4.0, it's a whole lot more powerful. Next time you hear about a 6.0 on the Richter scale, you'll know that's not a score for a dance competition. So, can we predict when these earthly jitters will occur? Unfortunately, not yet. Now you might be thinking, why can't we just mark our calendars and prepare for the big shake? Well, despite the leaps and bounds in our understanding of Earth's seismic activities, predicting the exact time and magnitude of an earthquake remains a challenge. Scientists can pinpoint areas of high seismic risk, such as the Circum-Pacific Seismic Belt, also known as the Ring of Fire, and the Alpide Belt. These are the Earth's hotspots, where tectonic plates love to throw their weight around. But knowing where the party's likely to kick off doesn't mean we know when the music will start or how long it'll last. Earthquakes, much like a spontaneous dance-off, are unpredictable. They can occur without warning, leaving us to deal with the aftermath. As we continue to delve into the dynamic and complex world of seismology, we hope to develop methods to foretell these natural phenomena more accurately. Until we crack that code, the Earth will continue to surprise us with its impromptu dance sessions. Stay curious, stay safe, and as always, keep exploring.